Probably just leave.
All right. Okay. Welcome. I'm Joe Anderson with the University of New Orleans REU in the track program, and I'm here with Colin O'Byrne and Brian Lewis for the present our results halfway through the FISH project. So what we're going to go through, first we're going to go through the basic project ideals, and the components that we broke it into was automatic thresholding, feature extraction, and classification. So the three of us will go through our different parts of the project. And I worked on automatic thresholding, and for the overall goals of the project, it was to use underwater video data to identify fish in local habitats. And so we need to use background subtracted images and produce images of identifiable fish so we could extract their data and work with science agencies. And to threshold these images, thresholding is basically to analyze the image and find the regions that are foreground and separate them from the background. And we do this from images from which the background has been subtracted. And so this is to remove noise and find distinct regions. So one of the methods we use is histogram analysis. And this uses a histogram of the image, which is a measure of how many pixels of a particular image are at a certain gray level. And this will take multimodal histograms, which means there are distinct peaks for different gray levels, and we'll find balances between them. Another method is clustering. And clustering will take the Gaussians of the different image data, and we'll match them and use them to find the optimal threshold. We use a method that uses the entropy of an image, which is essentially a measure of uncertainty, and the entropy functions we use will be maximized to find the threshold. And the graph cut method, which will model a particular image as every pixel will be a node, and different nodes will have weights between them, and you'll find the optimal separation of nodes, which will have the smallest cutting cost. So the methods we implemented specifically, the first one was Otsu's method, which is one of the earlier methods and often referenced as the most powerful method of its time. And it uses histogram analysis. And it will separate pixels of an image into classes, and it will measure the variance between those classes and will minimize that variance. And the next method we tried was an entropy method proposed by Guo, and it uses basic Shannon entropy principles. And it's another global threshold, which means it will operate over the entire image. And as we said before, the entropy is maximized. And Zhao's method, which uses a different type of histogram. It's a two-dimensional histogram. And the way they construct it, it has the level of pixels, the number of pixels at a particular gray level, but also the second dimension is how many pixels at a particular gray level have similar neighbors. So they construct this, what they call gray level spatial correlation histogram. And it's used, which takes into account local windows. So it incorporates local data into the algorithm and uses entropy methods to maximize that, multiply it by a weight, and then you can get your optimal threshold. Another method we used proposed by Ajlan uses, as opposed to the Gaussian methods used by previous, focuses on gamma distribution using Poisson models and minimizes the entropy, cross entropy of an image to find the optimal threshold. And the graph cut algorithm we implemented was by Tao only a few years ago, and it uses a faster version of a brute force graph cut method. It essentially creates a lookup table of all cuts between two distinct classes, and so it's able to create a graph cut algorithm dependent on the number of gray levels rather than the number of pixels. So they optimize the graph cut method a little more and also by using a normalized cut, which would remove the bias of using a small cluster of nodes instead of larger ones. Now, some of the results we achieved, you can see on the left is a single frame from fish data, and on the right side is the results using Ageland's method, which is the one that used the gamma. And here we have Otsu's class variance and Shao's gray level spatial correlation results. And you see they get a little better, but not quite the whole fish. And this is before any post-processing. The background has been subtracted and smoothed over to remove any noise. And then they've been thresholded. And what you get after thresholding is essentially a binary image. So these regions would be bright white and then black. And then we just substituted in the original where there was white. And finally, Guo's entropy method and Tao's graph cut method yielded fairly good results. And this is on a broadside view of a fish. But they also performed better on images where fish were casting shadows or were turned at angles. But they also suffered a little bit because they were a little unstable in regions where there wasn't a lot of fish data. And so there weren't a lot of nodes or a lot of entropy in that area. So they kind of got discounted and factored out as background. So they did have problems, but on what you might say is a better view of a fish, they performed very well. And that was image thresholding, and now Brian will talk to you. There's the bottom button. That's all right.
I'm Brian. I'm going to talk a little bit about feature extraction. So first we're going to talk about kind of the basics with features. They're almost universally represented with what's called feature vectors. It's essentially just what you think a vector. It's a bunch of numbers. Each vector can either be for representing one pixel in an image, or you can also have a feature vector for an entire image. And so if you have a feature vector for an entire image, it could either be made up of feature vectors for each pixel, or each pixel could just have one specific number that you use some sort of equation depending on what feature you want to extract. And then the vectors from each image, you then compare them to each other for classification. One of the common ways that people will start out doing classification, which Colin will talk about a little bit more about, is Euclidean distance, but there are certainly much more complex ways to do it. So some of the feature types you can do, obviously if it's an RGB image, you can work with color, RGB values. You can also do texture. For faces, texture is very unique also. Obviously with fish, the texture, the scales, even though it is an image through water, we can look at that texture and see what the difference is between fish species. You can also do shape, Fourier descriptors, do edge detection to compare the different shapes of different species. Also luminance can be a big one. For the fish project, luminance is kind of a difficult one, partially just because the lighting is not great. And as you saw with Joe, the lighting itself also causes issues with the background substitution. So it's not, because the lighting's not controlled, we can't do a great job with luminance in this case. So how feature extraction is done, you'll take your input image. In our case, what we did was Joe did the background substitution, and then each fish image in an original image is segmented. So for example, in the images he was showing, you saw about 2 fishes, and those were each broken down into the same size images. I believe it was 281 by about 121 pixels. Each image, before you pull out feature vectors, has to be the same size so that any, for example, distance measures or any sort of computation between 2 images is done that the pixels match up, or in reality the feature vectors match up. Otherwise you have issues where you may be comparing the tail of the fish, some information from the tail, with the head of the fish, and that'll obviously introduce a lot of error. You can also obviously, then once you've done that, we can use different filters, Gabor filters, produce some texture. You can do Gaussian, pretty much any image you think of, or any filter you think of that you can run over an image, you can use to extract features. Now they may not be great features, but you can pull features that way. You can also just do like straight RGB or grayscale values. You can also manipulate the color pixels in various ways, like luminance and stuff. And then one of the big ways, and that's the way we've been kind of heading, is Fourier descriptors, using them with the shape to help classify the fish. So using the Fourier descriptors, there was a paper that was done recently. They introduced a method called warp. And it uses Fourier descriptors, but it allows for different sizes of fish. So like if the fish is farther away in the image, so it's smaller, like it reduces any noise you may have because of the different sizes. Also, if the fish is rotated in a different way, it can also take care of that problem as well. And kind of just the basics about it, it uses a discrete Fourier transform to do that. And then what it does is you preserve the phase information. So because normally the phase information, they try to have some invariance in it so that everything worked, so that the image is all the same, but you actually keep the phase information and then you modify it slightly so that you can account for the rotation, so that when you're running the classification, hey, this fish was rotated 80 degrees, but otherwise the Fourier descriptors are the exact same. And then to actually classify the fish, they use dynamic time warping for it. So to run warp, the process you go through is you do image pre-processing, which would be background substitution, if you want to clean the image up, remove any holes, all those sorts of things to get the image perfect. Then you use discrete Fourier transforms, which is also in MATLAB the FFT function. If you know of it, it's the exact same thing, and that'll give you your Fourier descriptors. But then one of the nice things and why we use DFT is we do dimensionality reduction on it, because obviously you could have 500 plus points on the edge of a fish, and that's not very efficient. So by using a dimensionality reduction, we can approximate the best number of points. And in the warp paper they did, they found that using 32 points through this method is the best way to classify the fish. And they do the dimensionality by, it's called an energy, like they call getting the energy. And what you do is there's a function in MATLAB called FFT shift, and it orders the numbers. And you basically take, it's kind of a test you have to do, but you do, let's say I want 16 points to try to do it. You're actually going to take the middle 16 points from the image, or from the Fourier descriptors, and then use those to classify the image. And then after you reduce the number of transcriptors, you calculate the phase values, you also normalize it, and then you use dynamic time warping to actually do the classification. So some of the problems that you're going to run into with this obviously is the poor background substitution. We're never going to get a perfect image unless we take the fish out of water, lay it down, and take a great picture of it on a plain background. So you're always going to have some issues with the background substitution. Also, fish oriented at unusual angles. For example, if the fish is facing the camera as opposed to swimming along the side, you may not be able to say if those two images are of the same fish. However, if you have multiple images of a head-on fish, then you could say that they're the same. And also, because this is with Fourier transcriptors, if the fish species are too similar, for example, if you have two species of fish that the body type is almost the exact same, but let's say the color or the markings on the fish are different, this won't recognize that very well, because using Fourier descriptors, it doesn't care what the color or texture of the fish is. So now talking about classification, Colin's going to.
All right, so the goal of classification is to take these features and actually determine what the species of the fish is. And so the approach we've been using is neural networks, which are a pretty common approach to classification. Very quickly, the way neural networks work is you present data that you know the answer to the network, and essentially the network learns to classify data it hasn't seen before. And so there are three main network architectures I've been looking at. There's the standard multilayer perceptron, which is the most common feed-forward network used. And convolutional neural networks and restricted Boltzmann machines are somewhat more complicated architectures that seem appropriate for this problem. And so in a multilayer perceptron, you have an input layer, some number of hidden layers, and an output layer. And each layer is fully connected to the layer that comes before it. And so you present your input and the network gives you an output. It's the simplest architecture, and it would be useful on especially extracted feature vectors and potentially raw image data, though the number of connections makes that more difficult. And so the convolutional neural networks are somewhat more appropriate for use on image data. They use a lot of weight sharing, which makes them much more efficient. And so the way that works is you have your input image, and you essentially run a convolution on it. And the convolution kernel is what your trainable parameter is. And so you can have many more layers and many more connections, but they share a same small set of weights, and so it trains much more quickly. And so in between your convolutional layers, you also have subsampling layers. And so the idea is that your first convolutional layer extracts basic image features, and then higher layers extract more and more complex image features. And then you use a standard fully connected layer at the end to do the classification. And restricted Boltzmann machines are a kind of different network architecture. Rather than presenting an input and getting specific outputs, the network learns to model your input data. So if you input something similar to what it's been trained on, it will output what it's been trained on. And so we were hoping that this would be useful for recovering partial data. For example, if part of the outline of the fish is obscured, it would be able to recover some of that Fourier descriptor information, or even the silhouette information from a raw binary image. And so I implemented the restricted Boltzmann network and ran some tests to see how it would work on incomplete and transformed data, since that's the application we're interested in. These are just simple geometric shapes, obscured to various degrees and then shifted and rotated. And the network is able to produce the correct output pretty consistently. It gets a little confused with the rotated circles, but the images are so low resolution that that's pretty understandable, I think. I also tried it on actual binary fish data, and the results are much noisier than we would like. I think it's probably a function of training time. Just today I had a longer run that ran overnight for training, and the results are a little sharper. But it's not as good of results as we would like for if it's going to recover partial image data. I also tested the convolutional network. In this test, we have vertical bars in overlapping image regions, and as well as shifted and rotated versions of those patterns. And so I performed two tests. The first one, the network was actually trained on half of the shifted and rotated data and tested on the other half. And it does perfect classification of those. And even when the network's only trained on the original untransformed data, it only misclassifies 6 of the 150 training or testing samples. And so that was really promising. And using it on actual fish data also worked very well. These are some of the images from my testing set. On the left are E. morio, and on the right are other fish species. And so there were 28 testing images. It's actually 14 images flipped horizontally. And it only misclassified 3 of the samples. But those samples are shown here. So these are probably the 3 worst samples in the data set. The top one is E. morio, but swimming into the camera and turning. And so it thinks that's something else. And the other 2 outlines actually don't look all that different from E. morio outlines. So those are somewhat understandable errors as well. So things I'd like to work on for the rest of the program is to investigate the RBM results further and try and improve those and figure out why the results are so noisy. as well as test the CNN more on a larger network or a larger data set. And then once we have extracted features, obviously test those as well using a standard network architecture. And deep belief networks are kind of an extension of restricted Boltzmann machines where you use them for actual classification. So I'd like to look into using those on some image data, see how that works. I think that's it. Any questions?
For your team to accomplish the whole face recognition and tracking, are you going to consider just a single image or maybe an image sequence like the video in the overall?
I think long-term, the
Okay.
idea is to use the sequence, and then with the tracking that's being developed, you can identify the fish as existing in the sequence, and then you only need to classify it once. But I'm not sure that that's feasible for this summer. So we'll probably focus on classifying just single frames.
Okay. And also, when you do like fish classification, are you going to use neural network based or from the raw image data, or you're going to use some extracted features like for descriptors as?
The plan is to try both approaches and see how they work, and potentially even combine them in some sort of ensemble approach.
I have a question for Brian.
Yeah.
Did you implement your feature extraction already? Did you test anything?
Not yet. All I'm up to now, because originally I had started like looking at kind of texture, also Gabor filters and stuff, and I pulled some features, but we haven't really done anything. But then Dr. Dimitrios had kind of and shown me the work paper, and so all I'm up to now is I haven't really pulled features quite yet. I'm still messing around that energy to find the dimensionality reduction I want to do, because it's kind of a guess. You go, all right, let's look at 8 of them. Let's look at 16, 32, 64 and see how close to 100% of the variance we can get. So hopefully in the next week or so I can actually pull features.
Yeah, Brian started with the partially with what Joe presented. Like he started with the original data, so he was trying to. I mean, those silhouettes. I mean, not the silhouettes, the grayscale versions of the fish. He was working with that and trying to fill in also the holes somehow. So he was running like an iterative dilation erosion kind of algorithm to fill this in. So he didn't present that part, but he did that part. He started with that and then he switched also. Also, yeah, I can say that because I know that both Joe and Colin and Brian, I mean, they're implementing the things in themselves, and not just for future reference. I think maybe it's a good idea to say that, for example, I know that Joe implemented everything from scratch. For instance, the same thing with Colin. He implemented everything from scratch, whatever it present, even the networks.
That was my next question.
Yes.
If the work, I mean, if you had to code all this, or you just run a MATLAB function or a C code that somebody else coded?
No, they didn't.
Yeah, most of it was, I mean,
There are
the only
some-
thing I started to code, but then later I found out there was a MATLAB function was
They used to compute.
the gamma.
Oh, the gamma function.
Yeah, gamma distribution.
So
was-
yeah, they're using stuff like, for example, Joe is using probably that. He's using the function histogram, but no, yeah. Colin, you wrote the whole thing, right? I think from scratch, the multi-layer thing. Yeah.
Yeah.
And Brian is doing. Yeah.
Are you using the neural network toolbox?
No, I'll probably use that for the standard MLP since it's already built in, but I wrote my own MATLAB code for the convolutional network and Boltzmann machine. They're not actually implemented in the toolbox. So.
I have a question for Joe. You talked about the variance among pieces of the histogram. Can you explain that a little more?
Yeah, I guess I can draw one. The way Atsu approaches it is particularly if you have a bimodal histogram. So this is your gray level 0 to 255 for grayscale. And then this is your number of pixels, so we go up to 30,000 for 256 by 256. And you typically get like a lot of darker pixels maybe, and then maybe one for that. It would calculate these variances. Like you do a linear search through every possible threshold. So you start with threshold 0, and then calculate the variance of class greater than 0 and less than or equal to 0. And so you go through, and you would find the minimal variance would be here. because you have this class and then this class, and you'd have this variance and that variance. And so the difference would be minimal.
Okay, so you're minimizing the variances of each piece of
Yes.
after it's separated.
Yes,
Okay.
and yeah, you try every threshold essentially, and then just say which one was the best, we'll take that.
Okay. Thank you.
We also discovered a lot of papers had typos. In Joe's case, it was a lot of them.
I'm not gonna say anything.
Any conflict proceedings?
No, it's not. Very fundamental mistakes. For instance, the variance, instead of being the sum of, say, x minus the mean square times the PDF, it was without the PDF, for example.
There were some copy and paste bugs.